morning, welcome back to the studio. So in the previous session we had a lab demonstration, we saw how grinding was being done and we saw how MQL setup was made. We saw how various machining parameters were given as input and various factors were recorded. How do we recorded the sound? The air particle collector recorded the counts of the air particles on different sizes. The forces were recorded by LabVIEW software. So I left in the previous session at this state. So we had the kind of forces here. So these are the kind of forces. So this can be used, and I will plot this one using a line diagram and see I have this kind of setup. So this is another example. This data is actually from a drilling process. So in that process we had 4 holes which were through holes, and this kind of data was produced. So this data is generated. So what is essentially happening here? So this is my torque. So in this case I have taken only one hole here. So in the lower curves are the torque. So this is my drilling torque. You can see the torque is of the order of, if we start from 0, this is the order of 20 newtons, and this is my drilling thrust force. If I take this difference, this is of the order of 420, 680 minus 420, it is of the order of 260 newtons. So this is the drilling process. So what is happening here essentially, at this point the machine spindle is off. Machine spindle is off, that is why the force is constant here. So at this point we just switched on the machine spindle. If you remember, the M code for switching on the machine spindle was M03. So in our CNC code we put this code in our CNC program and the machine spindle gets on. So we can see this much rise of energy is there with spindle on position. Now this much load is there. So at this state, if this is my workpiece and I need to do a hole along this axis, and this is my drill. So drill has still not even touched my workpiece, but just for the rotation of the drill here, the spindle on, this much energy is there. So this is actually a kind of fixed energy. By force I mean energy here. So as we do machining, the variable energy would be rising. So this is my variable energy, this difference is my variable energy. This is also actually variable because this is also actually variable because this only comes into picture when we do machining. Just before starting the actual cutting, the spindle is on. So this is also a part of variable, but this is my force or my area of interest here, this one. So we see 260 Newton force is produced here. So at this point the tool tip starts cutting. So in the beginning the force is higher, so there is also variation in the force. So this force is there. So at this point the cutting, so in this, during this time, this is time here, during this time the cutting process is going on. So at this point, so in this process, at this position, the drill is here in my workpiece and the cutting process is going on. So at this point, cutting is almost complete. So my drill is like this. So this hole, through hole is made here. This is my workpiece. This is drill axis. So here also the cutting is completed, but the spindle is still on. Spindle is still in on position, and if I switch off my spindle, this thing would come down to this position again. This is again spindle off. So this was my cutting force. In this sheet I have the output from my sound meter. This is one machining process or one treatment. So you can see that 15, 44, 19, then 20, 21, 22, at each second pulse the recording is being carried out. So this is my sound recording at this point, at these points. And again in the second machining treatment here, these recordings are there. So using these recordings, we can take an average value and peak value here. So average value of all these would be about I would say 59, and average value would be 59 here, and the peak value, average value we can see. So we can find the average value, that is, if I say this cell is equal to average of these cells, or this is the average value, which is 59.35. Now I say I am also interested in the peak value of this. So I would say this cell is equal to maximum of this data. So let me give me the highest value, that is 60.1. In this specific situation here, in this specific treatment, the peak value is very much close to the average value. So there is not much variation. In certain cases, the peak value would be very high. For example, in this case, if I do the same kind of evaluation for the second process here, I say this is equal to average of these cells of my second treatment enter, this average is 69, but if I say peak value would be high here. I think it is about 98 here. Enter, see the peak value is this much. So these two values are of my interest here. So this was my sound meter output. Next I have my laser air particle collector. So this is the pulse here, the time, sample time at which the sample is being collected, and we have the counts here of 0.3 micron size, this much number of particles is there, of 0.5 size, this much number of particles is there, of 1 micrometer size, this much number of particles are there, of 5 micrometer size, 144 particles only. So, you could notice here that as the size, particle size or particle diameter is increasing here, the number of particles are very less. So, what is happening here is, this is my particle dia and this is my total counts. So, the total weight would be the product of my volume of the particle and the count of the particles. In that case, we can say even these 4 particles of 10 micrometer size might have larger weight than big number of 0.3 micrometer here. So, what we are interested here is in micrograms per meter cube. So, we have converted that into those units. So, this is microgram per meter cube. So, this is microgram per meter cube of these particles. So, this is PM1, PM5 and PM10. This column is for PM1, that is the particles. So, I have taken the cumulative sum of the particles here, and cumulative sum of the weights of the particles is taken, and these are the weight of the particle in micrograms per meter cube, that is below 1 micron size, and this one is the weight of particles in the same units microgram per meter cube, that is below 5 micrometer size, and this one is PM10, the weight of the particles in microgram per meter cube, that is below 10 micrometer size. So, this is my aerosol data, and these inputs, these are the inputs. In the present case, I will use only this input PM10. These inputs can be put into my analysis part. So, this was all the data. Now, I will come back to my presentation here, in which we will develop a smart factory. So, if you could recall, I had certain steps into that. So, these are the contents and also the steps to develop a smart factory that we have followed here. Live experiments are conducted. We showed you the grinding experiments in the laboratory. I showed you the demonstration videos of milling and drilling experiments as well, and also we have chosen one modern process, that is micro WEDM, that is micro wire electric discharge machining. Now, data analysis would be done. Then data analysis is using all the data that is generated through our various instruments, that is force, then aerosol concentration, that is PM10, this is force F, then sound intensity, this has two categories here, two variables here, that is average sound and peak sound, and also a quality parameter, that is surface roughness. RA. So, these are taken into account. Then after data analysis, the models are generated, regression models are generated here. Regression models. I would suggest here that if you are not a technical guy and you do not know much about the statistics here, however, Dr. Deepu Philip is trying to cover this one. So, please do not try to go deep into that how these models are generated. Just have a holistic view of this one, that what is the process or what is the procedure to obtain a green factory. So, if you are interested in reading, we can provide you the various references from where you could read how these experiments, how the data analysis is conducted, what is if we say optimization, we have used artificial bee colony algorithm, what is that, and details of that you can see. We can even learn the C++ programming which was used to write the code for artificial bee colony here. So, any details, any depth you can go in. However, the holistic view here is just these steps, the broad view here. So, after optimization is carried out using artificial bee colony algorithm, ABC algorithm. Then validation and time study. Validation is again live experiments. And time study is carried out using a stopwatch to find the machining time here. Then this time is the input variable or input phenomena for my smart factory. This smart factory will obtain by using Technomatic software. Technomatic software, which is part of PLM software, product lifecycle management software, that is developed by Siemens. Then factory simulation results would be discussed. So, this was the live experiment here. So, in the grinding we had parameters. Grinding wheel speed was 20 meter per second, which was 1500 RPM, and the wheel dia was 300 mm. That brought down the speed to 20 meter per second here. So, these two variables are selected, depth of cut and table speed. So, depth of cut had the discrete and continuous value. Now, you well understand. So, it has 2, 10 and 18 micrometers values. Table speed has also had 5, 10 and 15 meter per minute values. Coolant flow rate was 4.5 liter per minute in case of flood, and MQL flow rate was 20 ml per hour. So, this was my MQL or near dry machining. This was also conducted using vegetable oil. So, in the normal case mineral oil is used, that was also used for comparison. So, this is the analysis of variance result for my force, surface roughness, average noise intensity, and peak noise intensity. And also I have my PM10 value. So, before coming to ANOVA, I would like to show my data, input data that was there. So, in case of grinding, this was the input data. So, these are all treatments. So, this is full factorial design was chosen. Full factorial means all the experiments were conducted. All the combinations, all the possible combinations are used as treatments, and the experiments are conducting accordingly. So, this is the data for dry machining, data for flood machining, for MQL machining, and for MQL machining using a green fluid. This green fluid here is my vegetable oil. This fluid here is from M, it means mineral oil here. So, for all these cutting fluid methods or the all these cutting environments, the values were obtained for force using LabVIEW software, for average roughness value. In this case, for roughness 10 values were taken and average of those 10 values is put here. Sorry. And this is my sound, average sound for each treatment here, and peak sound here for each treatment, and PM10 value. This is the value of the aerosol particles, those are there. So, in case of dry, there wouldn't be aerosols, there would only be metal dust. So, this metal dust is of the order of 600, start from 200 to 1000 micrograms per meter cube. In case of flood, we can see that it is low. We'll look into it when we do the analysis, and we'll also see the differences and try to find the reasons why this difference is there. So, this is analysis of variance for force. In the analysis of variance, so it is the F value that decides the dominant variable here. So, in this case, this variable D, depth of cut, has maximum F value, that is it has maximum influence on my process, on the force here, and these P values are all significant till this point because these are less than 0.05, that is for at 5% significance level these are significant. So, these interactions, some of the interactions like this interaction is not significant, this value is greater. So, for surface assessment also we can see that depth of cut here also is a dominant variable. For average noise intensity, we can see that table speed is a dominant factor, and for peak noise intensity we can see that again depth of cut is the most important variable here, most important parameter. For PM10 value or for air particle concentration in the machine shop, it is the medium that has effect. So, across the that is within my this category, there is not much change, but the medium, that is for dry, for flood, for MQL using mineral oil, and for MQL using green oil, there is significant difference of variance here. So, this is my setup which we even discussed in the previous lecture. So, again putting down the cutting conditions here, these were the 4 instruments used. This is my dynamometer that recorded the force. This is roughness tester that recorded my roughness. This is my sound meter that recorded the sound. This is laser to particle counter that recorded my air particle concentration. So, workpiece here is duralumin, dimensions of the workpiece is this, and wheel is Al2O3 abrasive. So, this is the specification of my wheel, vitrified bond is there, and this is my wheel dia and width of the wheel. So, these were the cooling mediums. So, these are the cutting force. So, D is equal to 10 micrometer, we can see the tangential force. The tangential force, that is when plotted against table speed, we can see there is an increasing trend here. That is with the table speed, at higher table speeds in this range from 5 to 15, at when the table speed is increasing, the force is also increasing, and we can see that in dry, flood, MQL and MQLV, our purpose is to minimize this one. Our purpose is to minimize this one. So, we could see that this MQLV has best performance here, it is showing the minimum force here. So, in case of tangential force, when plotted against depth of cut, also we can see MQL with vegetable oil, here MQLV is same as MQLG, this is vegetable oil or green oil. So, in this case also we have found the similar pattern. So, in case of surface roughness also we can see that there is some interaction of MQL with vegetable oil with flood, but in the overall scene this is showing better performance here. So, then we obtain the regression models. These ANOVA results brought to us the regression models here. In this, the regression models are obtained for different cooling mediums. So, this is one of the way regression models can be obtained, and this is only for FT, for force only. We can see these are all kind of parallel lines with MQLV having minimum intercept value. So, this is selected to be taken forward to our optimization step. So, in this case these two factors are selected here which were taken forward to the optimization step, that is force and roughness are taken to the optimization step. So, coefficient of determination tells us the closeness of this model to the obtained result, that is this model is 95% close to the result. So, there might be some error there as well. So, this is also about 95% close to the values those are obtained. So, this value in case of machining has to be greater than 95%. In case of modern machining, it is also sometime more should be greater than 99%. Otherwise, these models are not considered. But in this case, we will take these models forward to the optimization step. Now, in case of noise intensity, this is my average noise intensity. We can see that the dry machining has minimum noise here, and the maximum noise is for MQLM. The reason for this one could be that in flood we have noise from pump, and in MQL because the pressure type system was used, so we also had a pump and we had air flow, that is compressed air. So, the average sound was the continuous sound was coming from the pump and air flow, that is why in MQL this sound was higher, and in case of flood the sound is even close to MQL here as well. But if I say in peak noise intensity, in case of dry the peak noise intensity is higher. Now, aerosol concentration, if you might have noticed in the data chart which I showed you, this dry machining had the aerosol concentration of the order of 650 microgram per meter cube, and this is lesser, this is going way higher, again this one is lesser. So, reasons for this, there is always physics behind this one. So, it is as a like systems manager, it is not always important to go behind the physics of this one. So, this is the job of materials engineer or this is job of manufacturing engineer, but to have manufacturing engineer in our team is also important, because sometimes this physics is very important, it is also determines our final factor, final selection. So, in this case this high aerosol concentration may be attributed to the dust, the metal dust that is generated due to the rubbing of my workpiece with my grinding wheel. And in case of flood, because this dust is flushed away, that is why this concentration is coming low. But in case of MQL, because spraying is there, that is mist is being generated, so the concentration becomes high. But in case of vegetable oil, the concentration is also high. It is lower than this one because the viscosity of this vegetable oil is lower. And also this vegetable oil, if it is inhaled, is not that bad as is my mineral oil. So this becomes my worst selection if we consider work environment as the criteria. So next we conducted ABC analysis, that is optimization. These are the parameters those selected for artificial bee colony algorithm, and weighted sum method was used. So this is one of the ABC method, and we find the convergence, and the final results were at this speed and this depth of cut, all the parameters were found at optimal state. So using these or selecting these parameters here, sensitivity analysis and time study was conducted, that is 5 replicates at this experiments were obtained, and we found that this is my force, this is my roughness, and these are the times for processing, times for setup of workpiece here. So in this case we found about 4% variation, in this case the variation was about 6%. So this is kind of acceptable. So these processing times were then taken forward to our factory simulation process along with the other processes, that is milling, drilling and micro wire EDM. So these are the activity times, those were recorded during the sensitivity or validation of our different processes separately. So this inspection is also instituted here. So in this case, in case of milling, drilling and grinding, processing times, normal distribution is selected, because the processes are found to be automated and only 5% variation is put in here. But in case of setup times, these jobs are done by human. There is large possibility of having human error or human constraint in this one. So in this case also the number of readings was about 5 only, 5 replicates were produced. So we chose triangular distribution. So there are different criteria to choose kind of distribution. We can choose normal, uniform, triangular, exponential, so it is actually not a day job to learn all the distribution and the factors. So I would again suggest that please look at the overall process. If you would like to learn that why and where triangular distribution is used, you can do additional study, but don't fall into the details during this lecture, and don't feel that the lecture is too heavy here. So before going to the results or of before going to the results of our simulation, I'll come to my technometric software and make you learn or would like to give you a kind of demonstration that how this software is used. So I will take a break here and we will come back to our lab demonstration session. This lab is not my manufacturing science lab. This is the Smart Systems and Operations Lab in Industrial and Management Engineering Department of IIT Kanpur, where we have PLM software, Product Lifecycle Management software, that is provided by Siemens, in which we have plant simulation software that we will use. This plant simulation, the other name here is Technomatics, that we will use to obtain our smart factory model. So let us meet in next lecture. Thank you.